Good morning, everyone, and welcome to Goblin Test 1.3 Integration and Interlinking of Knowledge Graphs. It's my pleasure to introduce today's speaker, who will be presenting Geospatial Knowledge Graphs, Interlinking and Question Answering, Professor Manolis Karparakis. He's a professor in the Department of Informatics and Telecommunications, National and Kapodistrian University of Athens. He leads the artificial intelligence team. He is also an affiliated researcher in the Archimedes unit of Athena Research Center. Manolis holds a PhD in computer science and from the National Technical University of Athens, an MSc in computer science from the University of Toronto, and a diploma in mathematics from the University of Crete. He is a fellow of Your AI, European Association for Artificial Intelligence since 2015, members of Your AI board since 2022, previous vice president and president of Hellenic Association for Artificial Intelligence, and member of the Standing Scientific Committee for the Introduction of Artificial Intelligence in the Justice System in Greece, March 2021 into today. He has published more than 270 papers that has been widely cited, 9,441 citations, and H-index 53 in Google Scholar. In the area of artificial intelligence, especially knowledge representation and constraints programming, databases, especially temporal and spatial databases, semantic web, knowledge graphs, and link data, especially geospatial and Earth observation data, and deep learning for natural language processing. His research has been financially supported with a total amount of exceeding 11 million euros by the European Commission, the Hellenic Foundation for Research and Innovation, and the Greek General Secretariat for Research and Technology, the European Space Agency and Industry. Professor Karparakis, your floor is yours. Thank you very much.
Thank you. Thank you very much for the generous introduction. Thank you also for the invitation. I'm happy to be here. I think Goblin is a very interesting project. So what I'm going to talk to you about today is question answering over geospatial knowledge graphs with a little bit of interlinking. I make this clear from the beginning. So this is my talk outline. I'll start with introducing geospatial knowledge graphs. I'll go quickly through some previous work on question answering over geospatial knowledge graphs. Then I will present the system TerraIQ, where I will tell you what we do about geospatial interlinking. And then I will tell you a little bit of about our current work in this area. So what is geospatial information? You see here a part of Crete, and you see the city of Heraklion here in the middle. In Google Maps, for example, we have a lot of geospatial information, right? And we use it every day. And geospatial information comes in many ways, many versions. So, for example, we can have qualitative geospatial information like cardinal directions. We might want to say, for example, that Crete is north of Africa. Or topological relations, we might want to say that the city of Heraklion is within Crete. And maybe we want to talk about distance and say, for example, that a particular village is near Heraklion. Or we can have quantitative information where basically we give the geometry, the polygons, the multi-polygons actually that correspond to Heraklion. And a geospatial knowledge graph is a knowledge graph that represents not just thematic, but also geospatial information. By thematic here, we mean basically non-geospatial information. So if the knowledge graph has an entity Heraklion, then the name of the city, its population, the current mayor, and things like this would be thematic information, and the geometry of the city or other information in qualitative or quantitative form would be geospatial information. So what are some geospatial knowledge graphs? I would like to claim that the Wikipedia is one of these knowledge graphs because it does have what I said earlier. It doesn't have rich geospatial information, but if you have, for example, the city of Athens, you have a lot of thematic information, but you also have this geometry, which is the center of Athens in lat and long coordinates. So in some sense, this is some simple geospatial information. Similarly, in Wikidata, if you have Greece, you have a geoshape. This is the construct that is used in Wikidata to capture the geometry of entities like Greece. Similarly, in Yago, in particular the version Yago 2, you have geoentities from Wikipedia and geonames with their lat-long coordinates and some topological relations implicitly. So, for example, if we know that a city is in a country, then it is within this country, right? So this is topological information, but implicit. In our work, and this is when we really started to see advanced geospatial knowledge graphs, what we did, we took Yago 2 and we extended with complex geometries from administrative geodata of Greece, UK, Ireland, USA, and also from the Global Administrative Areas dataset, which covers the whole of Earth, and some OpenStreetMap features. And in this way, we got Yago to Geo, and we used it in quite a few of the projects that we had in our group. After that, I mean, our publication was in 2019. In 2021, the group of Elena Demidova and Bonn produced the World KG Knowledge Graph, which basically makes OpenStreetMap data available as a knowledge graph. And the most recent geospatial knowledge graph is the Nowhere graph. This is a graph produced by the groups of Pascal Hitzler and Christoph Janowitz. And essentially here we have the integration of thematic and place-centric datasets into a geospatial knowledge graph. And this geospatial knowledge graph, like ours, has been used, like Yago to Geo has been used in many applications. Now, let me turn to the problem of question answering. So the problem of question answering is being able to answer geospatial questions that are expressed in natural language using qualitative or quantitative geospatial expressions. So, for example, what countries border Greece to the north and have population more than 5 million? Or what is the distance between Heraklion and Chania? So the problem here is how do we answer such questions? And actually the first engine that was proposed for answering such question was a system by Yunis et al. In 2012, where they had a spatially enhanced version of the Wikipedia, and they presented a method for answering particular kinds of questions over it. We went into this area firstly in 2018 and then in 2020 with my student Darmen Punjani, who developed an engine called GeoQA. And later on, we had a paper on neural methods for such question answering by Lee and colleagues. And most recently, we have some more question answering engines. I will present some of them now. So Hamzeh and colleagues from the University of Melbourne presented an interesting engine. They didn't give it a name, so that's why I give the name of the authors only and nothing else. But it's a very nice engine where you can pose a query in natural language. It is translated in an intermediate representation based on first-order logic using an object-based conceptualization of space where you have constructs allocation, place, event, properties, and relations. And then using templates, this is an important point that I want to make. Then using templates, the intermediate representation is translated into Geospatial, and it is executed over an RDF store, storing the knowledge graph. And in fact, they used Yago2Geo as the knowledge graph for their system. We introduced later on GeoQA2, which is a newer version of the GeoQA engine by my student Darmen Punjani colleagues, where the idea is that you might want to, so GeoQA2 addresses Yago2Geo. And in Yago2Geo, we have classes, maybe a class called county, class called river, a class called city, and instances of these classes. So we may have County Essex, or may have London, and we might have qualitative topological relations between instances of these classes, like the fact that London borders Watford, for example, or we might have thematic properties of such an instance, like population and county code, and also geospatial properties, quantitative ones in this case, where we have the geometry of an instance, and there is this property has geometry that connects an instance to its geometry, and then the geometry is represented with well-known text. And here is the software architecture of GeoQA2. We have it's a pipeline of components where we start with a user question here, and then we construct the dependency and constituency parse tree. Then we take the dependency parse tree, and there are components like the instance identifier, the concept identifier, and the geospatial relation identifier that annotate this dependency parse tree. Then the property identifier annotates it a little bit more. And then this annotated dependency parse tree, together with the constituency parse tree and the templates, this question answering engine is again depends on handcrafted templates. Using them, a query is generated, a Geospark query, and it is sent to the RDF store where Yago2Geo is stored, so that an answer is computed and returned to the user. I'm not giving you more details because I will talk about another engine in a little while in more detail. And the engine that I want to talk about is called TerraQ. It's actually a very particular engine in the sense that it targets the metadata of a satellite image archive. It was developed in a project called DA4DTE. This was a European Space Agency project where we had many engines. TerraQ was the engine that my group developed. And it was presented last year at the IGARS conference, which is a remote sensing conference in Australia. And because it targets metadata of a satellite archive, we first of all need a knowledge graph for supporting, for representing, for encoding such metadata. And this is the ontology of the knowledge graph that we use. So as you can see, we have images, and we have two types of images, Sentinel-2 that are optical images and Sentinel-1 that are radar images, and an image is a feature, and then a feature in these ontologies is also a feature in the sense of Geospatial, and rivers are also features, and seas are also features, points of interest are features, ports are features, and so on. This is the ontology. You have a sense of what we are able to represent. Then we took the metadata, and because the metadata was in other languages than English, we had to do a translation, and we used Mistral, the LLM Mistral, for doing the translation because it gave us the best translation ability. So then we had an English knowledge graph based on this ontology that we would pose questions over it. And this is the pipeline of TerraQ. Now, TerraQ is a lot more sophisticated than GeoQA2 because we were very experienced when we built TerraQ, and we did a very nice design. So as you can see here, and we will see the details in a minute, the first component in the pipeline computes the where clause of the Geospatial query that will produce at the end of the pipeline. Then we construct the ask select clause, then the query is generated, and finally there is a rewriting of the query that I will explain. The final query is produced. It's going to be Sparkle or Geosparkle. It is executed over the RDF store where the knowledge graph is stored, and an answer is given, and typically these answers are visualized. Let me show you an example. So this is the interface. The system is publicly available. You might want to say, give me 50 images of rivers, and these are the satellite images that you see here that correspond, or rather the first 5 that correspond, or the first 10 from what I can see here that correspond to the question, and in total they are 50. Okay, so let me now describe TerraQ in detail. As I said, the first part of TerraQ is constructing the where clause. Okay, and to construct the where clause, we take the dependency parse tree of the question, and we run it through the instance identifier. So if we have a question that says, give me 3 images of rivers in Italy with vegetation coverage over 20% taken after May 2020, then the instance identifier will identify Italy and will produce 2 conjuncts encoding Italy and its geometry, and this will be part of the where clause of the query. the corresponding query, the query corresponding to the question. Then we have the concept identifier. The concept will identify the class or the concept rivers in the query and produces similarly some triple patterns, a conjunction of triple patterns about a river and its geometry, and this will be part of the query as well. Then we have the temporal identifier that will find after May 2020 and will introduce it with a filter in the query. Then we have the geospatial relation identifier that will find in and encode it with a filter that contains the predicate SF contains from the geospatial vocabulary. And finally, we have a property identifier that will identify vegetation coverage, will map it to a predicate has vegetation, and will introduce the appropriate basic graph pattern and a filter condition in the question. Then we move on and construct the select or ask clause of the question. This is basically based on two modules, the return type identifier that is implemented with Llama 2, a fine-tuned version of Llama 2. This basically decides what kind of select or ask query it will be, and then the query form identifier here introduces the variables. So here Llama 2 will tell us that it's a select image. This is the type, but it's actually a select distinct with a variable image. Here, this is what the query form identifier tells us, and similarly with a query here where we need to use count. Then once we have these two, then the query, we have the where clause and the select or ask clause, then the query generator puts them together and introduces a Geospark query, as you can see here. And then optionally, there is a query enhancement phase that is responsible for correcting mistakes in the query. This is again an LLM-based neural query enhancer component. We might get, for example, a query that says select distinct where, but actually the most correct thing would be to say select average riverside as average riverside, because the query really is what is the average river size in France. And finally, the last step where we actually do a little bit of interlinking is materialization and query rewriting. The idea here is the following. When we have Geospark queries and we have in the filter clause predicates like SF contains, these apply to complicated geometries and they are very expensive to compute. So what we have done is we have used a geospatial interlinking tool that we have, and I will talk about this in a minute, to pre-compute the geospatial relations, for example, between administrative divisions, between sentinel images, and although we compute all pairs of such geometries corresponding to the administrative divisions Sentinel-1 and Sentinel-2 images, we keep only some of them. So the computation is manageable. And by some of them here, I mean that if we have, for example, that A is contained in B, then we don't keep that B contains A and so on. What happens here then is that instead of doing the computation about component, the contains relation is pre-computed, so we just pick it up from the knowledge graph. And as you can see here, for various questions, when before the materialization we had, let's say in this case, 27,000 seconds for answering these 13 questions that belong to this class, we get less than 2 seconds query response time in this case. So it's a very nice feature. And we have actually seen by going to presentations by people working on Google Earth and things like this, that whenever they also have to do something similar, they also pre-compute the relations because then it's very fast to answer similar queries. So what kinds of work we have done in geospatial interlinking? What we need in cases like the one that I just described is we have geometries like these that you can see here, G1, G2, I suppose this blue one here is G3, and then G4, geometries in Cartesian space. And then what we want to do is we want to discover geospatial relations between them. So between pairs of them. So we want to discover, for example, that G1 touches Z3, or G4 is inside Z3, or that Z2 overlaps Z1, right? So in general, we are given a topological relation R, a source dataset of geometries S, and a target dataset of geometries T. And what we want is we want all pairs, lowercase s, lowercase t, that belong to the Cartesian product of capital case S, capital case T, such that RST is true. And of course, we don't want an algorithm that is quadratic in complexity, but rather a more sophisticated one. So if you see the paper that is cited here, there is a system called Geospatial that we have developed. You can get it, it's open source, you can get it from GitHub, and you will see what algorithms we have implemented for actually doing these things efficiently. And to the best of my knowledge, in 2024, this was the state of the art in this area. Now, TerraQ has been evaluated on top of a data set called GeoQuestions 1018. That is a crowdsourced data set, the largest that currently exists for evaluating a geospatial question answering engine. And as you can see, we here give how good TerraQ is, or other parts, components of TerraQ are for doing class identification, or here, or named entity recognition and disambiguation. And on the average, TerraQ gives us 44.36 accuracy, which is not very big. It's better than the competitive query engines, but it's not very good in general. So we have actually worked on on a new question answering engine. This is our current work. The system is called Pythia. It's not a geospatial question answering engine. It can be used for arbitrary knowledge graphs. We have not added a geospatial component to it so far. And Pythia is based on an LLM-based single agent architecture that follows the React paradigm. And basically, you have here an agent that you see here in the figure. You see the agent in the middle using tools that do, for example, entity linking or property retrieval or query validation and execution so that we get answers. So this is the most sophisticated engine that we have developed so far, and my student Sergios will present it at KDD in August in Korea. Unfortunately, I will be on holiday and I will not be able to go. And so as you can see here, the F1 and hits at one metric in the case of Pythia or Pythia star, they are much higher. So the percentages here are much higher than what we get with TerraQ. And it's really trivial to extend this to a geospatial question answering engine. Okay. So this is all that I wanted to say. Again, thank you for the invitation. And you can find here our group's website. And from there, you can also get our publications and so on. And you can follow us in Twitter, on LinkedIn. And with this, I would like to close and thank you very much. Thank you.